All right, so we just spent a lot of time building up Bayesian adaptations to our small blind strategy for maximally exploitive shoving. And so now I think it's a really good time to compare the solutions I came up with, the solutions that we worked through, that we computed together for the different scenarios, for the different reads we have, the different Bayesian reads that we get, and compare it to Nash, compare it to the common solution. I mean, if you've ever heard a solution to push fault, I mean, it's Nash, right? Well, so let's see what the differences we get. So let's first looking at Nash, just to remind ourselves, at 7 big blinds, the Nash calling range. So villain should be calling open shoves with 49% of hands if he's playing Nash. The small blind should be shoving 66% of hands when it's shoving Nash. So that's the size of the different calling and shoving ranges for Nash at 7 BBs. So let's look at how Confier compares at 7 BBs, the different ranges we came up with. So we built a readless range in the last video, exploiting readless tendencies using a population model. And we found that we were using a 45% calling range for the population. That was the mean calling range that the population was using. So that was the size of the readless calling range. And the shoving range was 75% that we computed. That was the maximal exploitive shoving range we computed that, 75% of hands. So comparing that to Nash, we see that the villains are calling a little bit tighter than Nash, and so we get to shove a little wider. That seems to make sense. For the tight read, when we had a tight read, we actually put a read that villain was calling 39% or tighter, likely. That was our estimate for that. And so we found that we could be shoving 95% of hands. It was a very wide range. And then lastly, we also computed it for when we had a loose range, a loose read. For 51% calling, that was the loose read we came up with. That was what our mean was for the loose population. And we found that we should be shoving 63% of hands. So the tight range, I mean, when we compare that to Nash, we find that, again, villains are calling significantly tighter suddenly than Nash, 10% tighter. And so we get to be shoving a ton more hands. So this is good. The fact that our maximally exploitive range is so far from equilibrium, that this situation is so far from equilibrium, that means that, and we are choosing a maximally exploitive range, that means that we're going to be doing very well, much significantly better than if we were shoving Nash. And so, but what about the loose range? The numbers are actually suspiciously similar to Nash. We find that it's a 51% calling range, it's only 2% different from the Nash calling range, and a 63% shoving range, so only 3% difference from the Nash shoving range. So what's going on here? Let's look at these two ranges in more detail. Let's see what the ranges that we came up with were. What's the Nash range? Well, this is just Nash range. I just used Holdem resources and just made a little Nash range. Green means shove, red means fold. That's our range. And so this is at 7 big blinds. These are all the hands that the Nash equilibrium range shoves. And on the right is all the hands that the maximally exploitive Confier range shoves versus players on whom we have a loose read. And so let's look at how they compare and how they differ. So we can see that the Confier range is tighter. We don't shove quite as many hands. We saw that from the numbers. But let's look at the difference in the range. So what hands are we not shoving that Nash is? Or are there any hands that Nash is shoving that we're not? So we can see that Nash is shoving all the same hands that we are. That is to say, Nash is shoving at least the hands we are. It's shoving a few more. So it's shoving queen 2 off. But if we look at the numbers for the equity for shoving queen 2 off, we find that it's very close to 0. And again, 0 was the point at which decisions became profitable. So this decision is actually basically indifferent. That's very close to 0. These aren't chips. And so we're at 10-20 blinds. So, one chip is 1/20th of a stack. So queen 2 off is a shove. I mean, we're just indifferent. Nash says to shove it, we don't shove it, whatever. The range we came up with for the population was a little bit looser. So it makes sense that we shove a little bit tighter. Let's look at the other discrepancies. 8-6 off, 7-6 off. Again, these are, within one chip of being 0. So it's basically the same. Any other differences? 10-3 suited. Oh, wow, that's 0.04 chips. Okay. So that's not really different. 8-4 suited, that's half a chip. Oh, there's one. Okay, 6-3 suited, that's a little bit more than a chip. But again, that's a little bit more than a 20th of a big blind. So we actually ended up computing Nash, in a sense. We found an approximation for Nash, essentially. And we made approximations throughout this, but it's it's pretty startling that we came up exactly on Nash. And so it seems that the loose players are basically people who are shoving something like Nash or a similar size range. We see that there's a little bit different. They probably have more spread. And so the Cauffier maximally exploitive range that came up to shove that was basically Nash. So, that's really cool. I mean, I think that, that was something that I did not expect when I did this. I did not expect to hit Nash right on the button. That's really cool. That means we did something right. I mean, that means that the calculations we were doing were working and that we did set up the problem correctly and found correct solutions. But let's go beyond that. Let's see what this actually tells us about the population, too. So let's do some strategic population analysis now. So these numbers that we found give us strategic information, these differences in these ranges. So let's step back and remember that all this analysis was conducted on $100 PokerStars hyper heads-up sit-and-go population. These are all hyper turbos. They're all the $100 level. And so these results are actually, they talk about the population. And so what we found was that the population as a whole has calling ranges that are tighter than Nash. And so that implies that the population as a whole is exploitably tight. That's really good to know. That the population as a whole is exploitably tight. So when we're shoving Nash, readless, we're making a mistake. And we'll come back to that. We'll talk a little bit more about Nash. A tight read means that our villain is calling tighter than the population. And so what does this imply? Well, this implies that tight villains are more exploitable than the population, because the population as a whole was exploitably tight. So when we get a read that says tight, this is like the jackpot sound in your mind. It should be, because this is when we get to exploit the hell out of our villains, and this is when we can really make a lot of money, even though we're playing push fold, because they will be far from equilibrium, and so they will be very exploitable, and so our maximally exploitive shoving range will be really profitable. All right, so loose reads, on the other hand, imply that villain is playing closer to Nash than the population. And it ended up being startlingly close. Like, those loose players, a lot of them were probably shoving Nash, in fact. Or maybe some were just shoving wider than average, which, as we found, is just, essentially is Nash. Because the average population shoves tight, so a little bit wider ends up being a similar, at least, size range. But this implies that loose villains are less exploitable than the population. And that tells us a lot, too. So basically, whenever someone's calling you lighter short stacked than the average player, you're unhappy, because they're less exploitable, and so we're not going to be able to make as much profit from them, if any. So this brings us to the last sort of part, because, as I said, the standard solution to solving push fold is the Nash equilibrium strategy. And so what's funny is we've actually ended up finding it in this process. And we found sort of when to apply it. And so let's figure out when we want to be choosing the Nash equilibrium strategy. Let's figure this part out. So in part 4 in game theory in the video, we discussed different uses for GTO strategies, for game theory optimal strategies. The basic conclusions were that game theory optimal is best when we assume we know nothing about our villain's range, in a vacuum. If you've ever heard the term in a vacuum, that's this assumption. The other one is when villain is playing at or near equilibrium. Nash maximally exploits, the Nash shoving range maximally exploits the Nash calling range. So that's why it doesn't make, that's why it makes sense that when we found that maximally exploitive shoving range, it was maximally exploiting Nash calling ranges. And so, it looks like that situation is playing at or near equilibrium. And so it looks like, we might have found a place to use it. But let's make sure. So our population model gave us Bayesian information about our villains' ranges. So we can sort of cross the first assumption off the bat. I mean, I think that the first assumption is a terrible assumption. I think that's one of the reasons why so many people assumed that Nash push fold is the solution to push fold, because they assume that we know nothing about villains' ranges. But using our population, we were actually found that we know something about villains' ranges when we know that villain is playing $100 PokerStars Hyper Turbo. We actually do know information. And so we know that Nash is not necessarily best readless. We immediately get that information. And when we looked, our strategic analysis showed that the population of the $100 PokerStars Hypers was exploitably tight. So at these games, Nash is not the most profitable strategy readless. So you are making a mistake if you're shoving Nash readless. There's no ifs about it. We found that, at least at the $100 level. I mean, that's the caveat. We'll put some more caveats on the next slide. And so this also showed that players playing looser than the average play close to Nash. And so, in fact, Nash is therefore going to be one of the most profitable, in this case, the best strategy to pick in our situation for players playing looser than average. And so that's going to be the final sort of jigsaw puzzle to building this strategy. And so this is what we're doing. We're computing a dynamic Bayesian strategy for small blind push fold. This is what we've ended up finding. And so this strategy is going to work for any no limit, Holdem, heads up, sit and go, restricted to the following situation. Hero is playing $100 hyper heads up, sit and go on Poker Stars. It only works for that right now because that's the model I used. But when you do this on your own, you can put in your own model and it'll work for other, you can use it for your population. That's the whole idea, that this is applicable to you. And of course, Hero is small blind. We only did it for small blind. You'll have to work on your own to get some of the big blind stuff because I left that off as an exercise to the viewer. And lastly, we did it for effective stacks at 7 big blinds. In our readless ranges, we found a few others. We found it for a few other depths. But when building the final Bayesian dynamic strategy, we set stacks at 7 big blinds. Obviously, you might want to, that's something that might be easy to remove, but for now it is a restriction on our model. And so let's remember back to part 4, the game theory. The strategy that we're looking for is just a set of actions for every decision point we face, because that's a strategy. And so in this case, it's a set of shoving ranges for every decision point we face. And so I said it was dynamic. That wasn't just a buzzword. It's Bayesian because we use Bayesian statistics to solve for those, for some of the ranges, but it's dynamic because we'll be able to use it to adapt to our sample based on reads. That was the point of the Bayesian part, to make our strategy dynamic so we can adapt to reads and be maximally exploitive. And so let's define the strategy. We just use this following set of rules to define our strategy. If readless, shove using the maximally exploitive shove range at 7 big blinds versus the total calling shove range that we computed. We found that shoving range. We shove according to that when readless. When we have a read that our villain is tight, we shove using the maximally exploitive shove range at 7 big blinds versus that tight calling range. That was the Bayesian adaptation. We use that tight Bayesian adaptation, and we shove 95% of hands, and we make even more money than readless, maximally exploiting readless ranges. So we're very happy when we get a tight read. And then lastly, when we get a read that our villain is loose, when we have that read, the best option is to start shoving using small blind Nash equilibrium. Because chances are, if he's calling loose, he's calling at some near equilibrium frequency. And so when we shove Nash, we essentially make the most out of his mistakes. We win every time he makes a mistake playing Nash. If he's playing near Nash, he better be playing it perfect, because that's when he's doing best. And you're still making money. So when we have that read that villain's loose, we shove using small blind Nash. So we did end up needing it as part of our solution. And so, on with Coffey's maximally exploitive dynamic Bayesian strategy for maximizing small blind equity for push-fold poker versus the population of the Poker Stars $100 hyper turbo heads up sit and goes. Well, yeah, that thing, it's just on the next slide. I just didn't have enough room to fit the title for the slide. So let's just write on the next slide. We'll just go to it.